Hello and welcome to another one. So today's little video is going to be about the sort of why, if I integrate f dash of x over f of x with respect to dx, why do I end up with the natural log of the modulus of f of x plus some c? Now this question was brought to my attention by Tayyab Majid, and it is a really good question. He's got his own YouTube channel, so do go ahead and check that out. He does GCSE and also A level, and he's sort of venturing into further maths as well at some point, which I'll also be doing. He thinks he may be smarter than me, but you know, it is good to dream. How I'm going to tackle this question is by looking at this here. Now, this is basically a simplification of this in a sense. It's a lot simpler version of it. And if you can understand this, then there's absolutely no reason why you can do this for yourself. So I will leave this as an exercise for you to try once you've seen my video proving this. But if you're still struggling to see why that's true, then of course just leave a comment and I'll try and make a video on it for you. So the first thing I would like to say about this when I tackle a question like this is, well, I noticed that if I was to differentiate this function here, I should end up with 1 over x, and that would have to be true because differentiation and integration are opposites of each other. So in other words, sort of if you imagine the integral of 3x squared with respect to x, I know that the answer to that is simply x cubed plus some constant that nobody really cares about. But by the same logic that I mentioned here, if I was to differentiate the function x cubed, I should get 3x squared. So what that is basically saying is that if I was to differentiate x cubed with respect to dx, then I should end up with this function here. I could include the plus c in there, but I know that when I differentiate a plus c or some constant, it's just going to vanish, so it just turns into a 0. And so how I'm going to tackle this question is actually by answering the question. I'll give myself some space here. And I'm going to answer the question, or rather I'm going to prove that dy by dx is equal to 1 over x when y is equal to the natural log of this modulus. Now, the question that Tayyab actually asked me was, when you're sort of integrating and differentiating, or rather when you're integrating 1 over x, why do you get the natural log? Why is it not any other log to any other base? And the simple answer to that is because the inverse of the natural log function is the exponential function, and when you differentiate the exponential function, you end up with the same exponential function, and that's a simple answer. But if that doesn't satisfy you, then just continue to listen on, and you'll see sort of why it works. Now you might be wondering, why is there a modulus function around this? Why is there a modulus function within the log function? And the reason is if I didn't have that around the x within the log function, I'd be trying to say that when I differentiate ln of x, I get just 1 over x, and that isn't technically true, because the domain of the natural log function is, of course, x can only be positive, it can't even be 0. But the domain of, or the values that can go into here are, of course, positive or negative, again with an x, so we can't have 0. So why we have this the modulus around the x is so that now the domains of both the functions are exactly the same. So I can put a positive or a negative number into there, and I can also put a positive or a negative x in. And that's the reason, if you want me to make a video about this, explaining that in a bit more detail, again, just mention something in the comments alluding to that, and I'll try and do my best. One other thing to mention before I dig into the actual proof is the function modulus of x and what that actually represents. So the modulus of x, what that does is it takes whatever value you give it, and it gives the positive value of that original sort of number. So for example, if x was equal to 5, well then the modulus function doesn't actually have to do anything. It'll just tell you that the modulus of 5 is 5. But say x was equal to -2, then the modulus function has a bit of work to do. It has to now change this number and give you an outcome of 2. So really, in sort of in a formal way of saying that, what the modulus function does, I'll just put a circle around that so it's separate. What the modulus function is doing, well, if x is positive, or of course if it's 0, then the modulus function, like we said there, it doesn't actually have to do anything, so it'll just return the original number. It'll just give me x again. But, and this is the tricky bit that people tend to get a little bit confused on, is that if x is actually negative, then like we said, the modulus function has to do a bit of work, it has to do something. So the modulus function, what it's actually going to do is it's going to take that value, the negative value, and it's going to multiply it by a negative so that it turns it back into a positive number. So it's going to actually multiply it by -1. And so the modulus function is actually saying just take that number that you have if it's negative, times it by a -1, and you'll then end up with the positive, the size of that number, really. Hopefully that's making sense. All right, then, we're pretty much ready to jump straight into the proof. Right, so I'm going to start off with y equals ln of x. Okay, I want to get rid of this natural log, so I'm going to, of course, exponentiate both sides. I end up with e to the y equals mod x. All right, now at this point, this is where I'm going to break it up into my two cases. If you remember on the previous page, I said one case was where x was positive, or of course 0 as well. And the other case I'll do on this side, this is going to be where x is less than 0, i.e. where x is negative. All right, so when x is positive, we know that the function e to the y is equal to mod x, and that's obviously just going to be x. If you remember, we said that when x is positive, modulus of x is simply just x. What I'm going to do then is I'm going to now differentiate both sides with respect to y. I know the common thing to do is differentiate with respect to x, but this time we're going to differentiate with respect to y, and that's sort of part of the trick to this proof. If I differentiate both sides with respect to y, I get differentiate e to the y with respect to y, and that is of course just e to the y. Nothing actually happens there, and that's the main thing with this proof, really. To understand sort of the proof, you need to realize that when you differentiate the exponential function, you end up with itself. Sorry about that, my camera clapped out on me a little bit there. But what I was saying was that I'll just differentiate both sides here, and I'll end up with this thing here. Of course, when I differentiate e to the y, I get the well, exponential stays the same when I differentiate with respect to whatever variables in there. But on the right hand side, I'm going to get dx by dy, and that's sort of the crux of the proof, really. Once you've got that, you're pretty much home and dry. Right, the next bit is to then say, I'm just going to sort of reciprocate this, or upside down it if you want, dy by dx on this side. And on this side, if I reciprocate this side, I'm going to get 1 divided by e to the y. And then at this point, I'm just going to take this e to the y here and replace it with an x. And you're going to see that I get 1 over x equals dy by dx, and that's exactly what we were trying to prove. We were trying to prove, if you remember at the start, that dy by dx equals 1 over x. But we only really proved it for x is bigger than or equal to 0. So what we're going to do next, do exactly the same thing for this negative side. And it's going to be very similar, tiny bit different. This time what we've got is e to the y. Again, it's equal to the modulus of x. But because x is now less than 0, modulus of x is, as we said on the previous page, it has to be negative x. Right, again, same idea. I'm just going to differentiate both sides. Differentiating both sides gives me, again here, if I differentiate e to the y, I'm just going to get e to the y. If I differentiate minus x with respect to y, remember we're differentiating here with respect to y, we're going to get minus dx by dy. And at this point, again, I'm just going to reciprocate both sides, which is perfectly valid. I'm going to get 1 over e to the y is equal to minus dy by dx. And now what I'm going to do is take this e to the y, and I want to switch it out for the x up here. So I'm going to replace this e to the y with minus x. I'm going to get 1 over minus x is equal to minus dy by dx, and multiplying both sides by a minus 1, I get 1 over x is again equal to dy by dx. So we've proved, whatever the correct English is, that no matter what value x takes, whether it's negative or positive, and also if it's 0, we are always going to have that when I differentiate the function y equals ln of mod x, I'm going to get 1 over x. And so we've proved that if I integrate, therefore, this function 1 over x with respect to x, I'm going to get the natural log of the modulus of x plus a constant term. And that's really all I've got to say for today. Goodbye. Thank you.